Welcome back to our final segment. We're still discussing, the conservation of charge, as well as the fact that, once charge remains constant and two materials are involved, there is the transfer. And the transfer actually speaks to the quantization of charge, which has a lot to do with the number of electrons either lost, gained, which effectively talks to the number of electrons transferred between two materials during a physical process, which is the contact. Right. Now, we're still talking about this scenario that after separation, they retain a same amount of charge. And you'd realize that the force that acts on, we say this one is QA, and then this one is QB. The force exerted by QA on QB is away from it. Why is it so? Because these are actually like charges. Okay, so the idea of the force as a vector is very important, because we know that charged particles or charged materials, they exert a non-contact or a field force on each other, and the force could be in the form of attraction or repulsion. Now let's shift gears a little bit and look at a different scenario altogether. And you'd also realize that the units, they keep changing. But in this scenario, based on our prediction, something's going to be a little bit different, because we want to predict, once again, what would happen if a charged object is brought into contact. So we can't talk polarization here because there is contact. So transfer of charge will actually take place. But this other one is neutral. So let's call this one, let's label this one Q1 and this one Q2. So what's the difference between Q1 and Q2? Q1 is negatively charged. It has got excess electrons. Okay, why? Because it's negatively charged. Then Q2 is neutral. It has got a zero net charge. What does it mean? It means the number of electrons on sphere Q2 is equal to the number of protons, hence the net charge is zero. But it doesn't certainly, necessarily mean that it does not have charges. The net charge on Q2 is zero. So there are no excess electrons, no excess protons. Why? Because the number of protons equals the number of electrons. Okay, that's the main thing, right? Of protons is equal to the number of electrons. Okay, that's the main thing around a neutral material, and it speaks a lot about the origin of charge, as we had in our earlier discussions. Okay, so here the net charge is definitely going to be Q net, okay, just to put it out there, is equals to Q1 plus Q2, right? So Q1 is negative 9 millicoulombs plus 0. This gives us what? Negative 9 millicoulombs. So that's our Q net, right? So as long as this is a closed system, the net charge is not going to change before or after the physical process has taken place, right? And then after separation, this is what we have, okay? Now, remember, the moment they start to share charge, one that has got excess electrons, if you can quickly go back to that, you see this one has got excess electrons, Q1, okay? So that's why electrons are transferred from Q1 to Q2 during that physical process. Now, we are saying that now that they are identical, or now they are alike charges, they would exert a repulsive non-contact force on each other, okay? But still, we maintain that Q net is equals to, okay, that's still our Q1, and then that's our Q2. Our Q net is negative 4,5 plus, okay, negative 4,5, okay? It takes us back again to negative 9 millicoulombs, okay? So that's our Q net. So our Q net has not changed, okay? Right, so it means the principle of conservation of charge is still valid, or still holds in this case, right? Now, what are we saying in a nutshell? We're saying that the law of conservation of charge states that the net charge, so the net charge is one of the key terms, okay? It should be in an isolated system, remains constant during a physical process. Okay, so and we know that for us to obtain, the new charge during a physical process, which is the same. This is the same as saying Q net divided by 2. Okay, because Q net is the sum of the two charges that are interacting. So this is actually the main idea in as far as conservation of charge. All right. Okay, we understand that. Now let's look at a typical problem and discuss the approach around it and how exactly we apply the principle or the law of conservation of charge as well as quantization of the charge, because we've put it out there that the two actually cannot be separated. Okay, it says two spheres touch. That's a physical process. There is contact. So once they touch, we are saying there is what? There is contact between them. And immediately we talk about contact or spheres, whether charged or not, we can talk about the transfer of charge, right? Now, which is the electrons. So the one charge is +4 microcoulomb, and the other one is -10 microcoulombs. They are separated on the charge on each sphere is -3 microcoulombs, okay? Determine the size of charge transferred. Determine the size of charge that is transferred. We want the number of electrons or the amount of charge that is transferred, okay? So we know that the law says Q is equals to N QE, right? So that's the principle, okay? So the change in charge is actually equals to the number of electrons transferred multiplied by QE, right? So we can determine the number of electrons because we are able to tell, okay, initially it was, one of them was that, okay, if that's our Q1, okay, and then maybe this one is our Q2, and then this is the Q new on each one of them. This is after separation. So what are we saying here? We are saying that the number of electrons that, which is the actual charge transferred, that's the charge that's transferred, is equals to delta Q over the elementary charge. Now, let's use for argument's sake Q2, okay? Finally, Q2 is -3, okay, times 10 exponent -6, okay? This is the final, because change is final minus initial, okay? The initial charge was -10, so it's minus -10 times 10 exponent -6, okay? We divide this by the elementary charge, which is, because Q2 has got excess electrons, it's the one that loses, so it becomes less negative or more positive. Hence, we'll ignore the negative in the elementary charge value and put 1,6 times 10 exponent -19, right? So here we are actually going to get a value that is positive because we can have a positive number of electrons. So the number of electrons transferred can be calculated in that way. Let's go to our calculator now, okay? From the calculator, okay, if we clear that, that's a fraction, okay? We are saying -3 times 10 exponent -6 minus, okay, minus 10, okay, times 10 exponent -6. We close that, and then we divide by 1,6. We ignored the negative because the Q2 is the one that has got excess electrons. In other words, that's the one that loses during the transfer. So this is the exponent -19. Okay, what does this give us? We go to our calculator, 4,375. Now that value looks very familiar because it's the same number of electrons that we calculated earlier on in terms of the number of electrons that were gained by Q1. So 4,375, okay? It's 4,375 times 10 exponent 13 electrons that were lost by Q2, right? So this is the change of the size of the charge that was transferred between the two, right? Okay, so determining the number of electrons, we've done that. It's always about the quantization of charge, which is N is equals to change in charge divided by the elementary charge. So that's the big idea in as far as the fact that charge is quantized. So the change in charge of both Q1 and Q2 during the transfer has to do with the number of electrons that were transferred. That's the main idea in as far as this problem is concerned, right? Okay. Now, in summary, what are we saying? The number of electrons transferred between two objects is based on the law of quantization of charge. So, number of electrons, okay, number of electrons lost, okay, is equals to number of electrons, okay, number of electrons gained, okay. This is also equals to number of electrons transferred, right? So for the charge to remain constant, the net charge to remain constant, what is lost during the transfer must be equals to what is gained. That's the big idea in as far as this problem is concerned, right? Now, let's look at some of the, real life applications of electrostatics, because electrostatics, in a broader sense, deals with forces, deals with charges. Now, what is it that we already know? We know that like charges, they tend to repel each other, while opposite or unlike charges tend to exert a force of attraction. Now, you'd wonder, in terms of everyday life application, how does this all come together as far as electrostatics is concerned? We are saying that, take for argument's sake, the photocopier, the ink has to be, during the printing or photocopying, the ink has to stick on the piece of paper. So if the ink is charged opposite to the paper, it means that the ink droplets can easily stick onto the paper. So the issue of the photocopier it also actually has a lot to do with the application of electrostatics. Also in industry, you think of spray painting. Spray painting, printing, uses more or less the same idea. The paint droplets are charged opposite to the body of the car. So once it sticks onto the car, that is made possible due to those non-contact, okay, non-contact electrostatic forces that exist between them before they even come into contact, okay? Non-contact electrostatic force. But in this case, in both cases, it's actually attraction, okay? It's actually attraction. So the paint droplets are actually attracted to the body of the car, while again, on the other hand, when you talk about, those processing industries on a large scale manufacturing, industries, you get where you've got smoke coming out of chimneys. So to exclude the smoke, from the plant, they also charge the smoke in a different, in an opposite charge to, the chimney, so that the smoke can actually be taken out of, the plant. So when that happens, we are still applying the same principle that opposite charges actually they attract each other, okay? While like charges, they repel, okay? So opposite charges, they exert a force of attraction. So that's the main idea. Okay, let's go back to our, our big picture to try and bring all these pieces together. Now, our discussion was purely based on, conservation of charge, right? To say that the charge, the net charge, as long as it's a closed system, remains constant. It does not change during a physical process. And what is a physical process? It's this, two materials that are charged, or one is charged, the other one is uncharged, because there's a variation of that coming into contact and being separated, and ultimately each one of them retaining an equal amount of charge. So that conservation of charge, again, speaks to the quantization of charge. So in simple language, if one perhaps is to talk about the fact that what do we mean when we say charge is quantized? Remember, for a material to be charged, electrons need to be either removed from it for it to get a positive charge, or electrons need to be added to it to get a negative charge. So the magnitude of the charge entirely depends on the number of electrons that were actually removed from that material or added. Okay, so if the greater the number of electrons removed from a material, the more positive it becomes. Okay, so it has got a greater positive charge than a material which has got a comparatively lesser number of electrons removed from it. And similarly, if we were to consider a case where electrons were being added to a material so that that material attains or achieves a negative charge, the magnitude of that negative charge is not the same because it depends on the number of electrons added. So the lesser electrons we add, the less negative it becomes. Okay? So if we add a lot of electrons, it has got more electrons in excess, then it is even more negatively charged. That's the big idea for us to say what it means when we say that charge is actually quantized. Right? So we also looked at the non-contact forces, because where there is charge, there are forces involved. And these forces are either attraction or repulsion. And the materials that are involved, we spoke of conductors and insulators. So this brings it all together in terms of what exactly happens when charged materials interact with each other. Having said that, I think we kind of get the gist of how all these little bits, come together to make the big idea of what exactly is involved in electrostatics. Hopefully that makes sense, okay, because we discussed quite a lot of concept. But I think because of time constraints, we shall call it a day for now. I hope it made a lot of sense. But the idea is to bring all these pieces of the puzzle together and create that understanding that is much needed. So for myself, Themba Ncube is cheers and bye-bye for now.